Today I want to talk about resonance, which is really cool. So I've drawn you two acetate ions. Here's acetate. And I want you to notice here that this oxygen has 6 valence electrons locally, so he's neutral, but this oxygen has 7 electrons locally, so he has a -1 formal charge. And on this side, that's up here. So all I've done is switched the configuration of the double bond. And don't forget, there's a carbon in the center. Anything that doesn't have a listed element here is a carbon. And there's a carbon on the end here that must have 3 hydrogens out like this. It's a methyl group. Carbon has to have 4 bonds, so unless I say otherwise, you can just assume from the end of that line being the end of a line that there's a methyl group right here. And this carbon, his double bond is to the top one, but this carbon over here is double bonded to the second one, but there's no actual reason for one or the other to exist. Both of these are absolutely possible because these structures are equally well configured. And when you look at acetate, you're not going to find one or the other. And if you were able to split them in half, you're not going to find half are like this molecule and half are like this molecule. You're going to find a hybrid of the two of these molecules. Let me show you what this looks like on an electron microscope. Maybe that'll help. Here's the actual cloud for acetate. So I want you to notice that these oxygens are sharing. They're sharing the electrons equally electronegative on this side. So when I draw these two structures here, we call them resonance forms because the double bond here, this pi bond, I'm going to make more of like a dotted line, and I'm going to draw it kind of like this instead. To show you something here, I want you to think of it more like, if I was to draw this flat, let's try and draw it, pretend it's flat on a 2D plane, like I'm just that good at drawing. I'll draw the oxygen kind of skewed. There's pi orbitals here, p orbitals, excuse me, in each of these spots. And that allows electrons to travel freely in this space, and at the bottom here too. Yeah, these orbitals overlap to form these pi bonds. So what you're going to find is, even though we have two different ways to draw the acetate structure, that tells us that there's going to be a resonance hybrid of the two of them. It's a really useful concept that we'll be going over and over and over, so don't feel like you have to understand it perfectly right now, but maybe some more examples will make it easier. If I was to draw like a benzene ring, let's do a benzene ring. That's a classic organic chemistry thing. There's a double bond drawn at every other face gap like this. But when you look at it in an actual microscope, you're not going to find that it's like stutter stepped. You're going to find that it looks like this. Electrons are free to travel about above and below this particular spot, because if I draw it flat, I'm trying to draw it in a flat 2D way here, these p orbitals overlap, and it allows electrons in this pi bond, which we draw with a double bond here, to actually travel along all of these p orbitals. It's like an information superhighway. We've talked about this a little, but it's very important to understand that therefore a resonance structure exists. There's no reason that I can't draw this exact thing, but draw it as the 3 being here, here, and here, and erasing these like this. You could do that. It's the same concept though, because they are in resonance. There's going to be a hybrid. So not necessarily do we think of this as being the double bond spot. We think of this as like everybody gets some bondage for the, that sounds weird, for the pi bond. It's way better to use your brain power to think of everything as being connected and sharing that second bond ship here. So of course in the benzene ring, there's the equivalent of 3 pi bonds across this whole space. Everybody here gets kind of like a half of a bond strength, except it works a little bit more complicated than that. It's quite stable because electrons have so many locations that they can hover around that they're always going to want to be able to reinforce each other in a positive way. Maybe positive's the wrong term to use there when we're talking positives and negatives. But it's very important, just as we're looking at this, to say something like, hey, These are the actual real world versions of what happens. So this acetate being drawn is not wrong, but it's not the complete story. You look at this one here and you say, okay, this is a resonance structure. This is a resonance structure. Like either of these are going to be 50% of the story. And you want to be looking for that because when you look through the microscope, or let's just say as you analyze chemicals, you're going to find that they absolutely share 50-50 power, each of these resonance forms. And when you combine them together, you get the correct picture of them. So let's make some rules. Rule number one. Rule number one. These are not real molecular representations. These are imaginary segments of the reality. This is half of the story. This is half of the story. Because the real molecule is both of these at the same time. It's a hybrid combination of these. It's like the weighted sum of all of the resonance structures. Okay? Rule number two. I'm going to write a big 2. Rule number 2. Resonance forms differ only in the placement of the pi or non-bonding electrons. Think about that for a second. Only the positions of the pi electrons and the lone pair electrons differ from one form to another. Sigma bonds don't do this. Sigma bonds are straight up electron locked in sigma bonds. Pi bonds do this because we show the p orbital overlap that allows them to bounce from spot to spot. And that also affects where the lone pairs of electrons go. That's very important. So here's what I'm going to do. I'm going to take this side of the structure. I'm going to show you how we use curved arrows to demonstrate resonance. Show these lone electrons being willing to form a double bond here, and then show this double bond being willing to become lone pair electrons here. And you notice from this side it's the same idea. It says the same thing. The perspective is just upside down. So what we're showing here is that electrons would be happy to form a pi bond on either side, and that they'll distribute that -1 charge between these oxygens through resonance hybrid structure. Okay, so now that's what curved arrows are for. Don't forget that's what curved arrows are for. Let's make rule number 3. Rule 3. Ready? Here we go. Different resonance forms don't have to be equivalent. Now these are. This is equivalent. And so would the 2-benzene be equivalent. But they don't have to be. I'm going to show you a different example. Are you ready? What we're looking at right here is acetone. Do you know what that is? Acetone. It's a cleaner. It's used a lot by tradesmen to get a lot of stuff out that water doesn't wash away. Let's look at what happens when you add a base to acetone. I guess real fast, let's just make sure that we remember. These are methyl groups, right? There's H's out here. H, 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 whatever it takes to get 4 bonds onto these carbons. And that's, of course, a carbon there as well. But we're chemists now. We don't need to see that. We know it's there. And this carbon already has its 4 bonds, so of course there's no hydrogens there. But when I add a base to it, here's what we make. Okay, now that I've shrunk them down, let's just write plus base with an arrow. And let's look at what it makes. Okay, so what does a base do? Bases add electrons to the situation. So let's add an electron to the situation. Maybe we can figure this out here. The first one I'm going to draw is going to look like this. Let's say that, let's just start with our acetone. And I'm going to take off that, well, let's keep that double bond on there. We'll just have this oxygen, just straight acetone right now. But we'll say that this carbon here is going to pick up extra electrons. And it's going to drop one of the hydrogens, and it looks like this. So the extra electron is here. You'll notice this carbon has 5 electrons around it, so that's going to be a -1 formal charge. Carbon only likes 4. So even though it dropped a hydrogen, it's still got too much sitting around, and these electrons may well want to attack and form a pi bond here with the carbon in the center. There are too many electrons on carbon. They might look for a new home. and form a bond here, at which point this carbon would be overloaded and say, all right, well, we'll just drop this onto the oxygen. And what you might end up with then is single bond on the oxygen like this with lone pairs out here. And this oxygen now has 7 valence electrons, so he's going to have a -1 formal charge over here. And this carbon is perfectly neutral, and this carbon is perfectly neutral. But there's only 2 hydrogens on this one over here yet, and it's double bonded. All right, I'll draw it like this. Double bonded now. We showed how that could happen from here. So when you look at these structures, one is a double bond on the carbon and one is a double bond on the oxygen. But the question is, which one would happen? Well, we now know that both of these happen at light speed, constantly back and forth, so many times per second. It's in the millions of millions times per second. There's no question that both of these exist together as a hybrid structure. So perhaps the best thing to do when you look at this is to think about it as more of like 50-50. Some people draw it this way, some people don't. I don't even need to get into it, but you can have your oxygen here. And the problem with drawing that dotted line is that what do you do with the electrons here? Do you put 2 here or not? Because here it doesn't have them and here it does have them. So there's no real perfect way to really represent it with this modified simplistic resonance system. The best thing to do is to draw each of these structures like this, and to show that they both can happen together. And then a chemist can look at this and say, oh yeah, okay, here's a double bond on the carbon, but over here there's a double bond on the oxygen. So these are resonance structures where the electrons are free to flow in this area here. And maybe it happens over on this side, but I think you'll find that that's identical to this representation over here. Okay, so that's a good example of how they don't actually have to be equivalent to each other like the last ones we looked at. But what about rule number 4? Rule number 4. Big 4, very important. Resonance forms obey valence laws. So what do I mean by that? It means that the octet rule still applies, at least in the second row. And I come up here and I go like, hey, when it comes to sulfur and phosphorus in row 3, they start getting heavy enough to do some weird stuff. But you're not going to see a ton of that this year, this semester, or next semester probably. So I won't stress it too much until that actual thing comes up. And just keep that in mind. They're still going to follow those rules. So look for octet rules. Remember, this oxygen still forms an octet rule with this 2 for this bond and then 6 here. So, and same for the carbon. So keep an eye out and make sure that you don't imbalance something in some ridiculous way. This acetate still forms those. So it's not like you can just put double bonds on this like this, because this guy in the middle here would have like 10 electrons accounted for. And that's just not going to happen. Okay, we're getting through the rules pretty quick. What about rule number 5? Rule number 5. Very important. The resonance hybrid is more stable than any individual resonance form. What does that mean? It means that these two merged concepts into a cloud of what the molecule really is more stable than what this particular molecule would be or what this particular molecule would be by itself. That's actually why it forms that. Everything in nature seeks the lowest energy possible. And when something is at the lowest energy possible, it takes more energy to disrupt it and bring it back out of there. You see? So by definition, having more availability to move around, electrons will find a lower energy configuration than any one of these individual aspects. That's really important to keep in mind. Like with benzene here, if you had, and you can do this, I'm just going to draw a fast hexagon. If you form double bonds this way, well, aside from what's going on with this guy, you could do that. And maybe it breaks open. Maybe we'll just draw it like this, one here and one here. You could do something weird like this and just have the hydrogens fill in the difference. But it is not going to be as stable as what's happening with the benzene here. This is not benzene. This is something else. They'll have a name for it like 123 something hexene, cyclohexene or something like that. It doesn't matter. But it's not going to be as stable as the resonance structure that you form from a benzene ring here. It's just not. This allows electrons to go everywhere. And in so doing, they find the lowest energy configuration between them all on their own. That's kind of a law of entropy. Okay, those are the 5 laws of resonance. And I think we're in pretty good shape to actually start drawing some of these resonance forms. So in the next video, I'll actually show you examples of this. This is just a quick run through.